Hi everyone, my name is Majid Namazi and I am a PhD student at Griffith University. I am going to talk about surrogate assisted optimization for traveling thief problems. Traveling thief problem is a combination of two interdependent NP-hard components including traveling salesman problem and knapsack problem. In this problem, items are scattered over the cities. A thief makes a cyclic tour through the cities. Using a collection plan, the thief collects items into a knapsack. The knapsack is rented and the knapsack has limited capacity. As the items are placed into the knapsack, total profit increases and total weight increases, but speed decreases, so the traveling time and the total renting cost increase. TTP goal is to maximize total profit and minimize total renting cost. So objective value is computed as total profit minus renting rate multiplied by total traveling time. Cooperative TTP solvers include methods such as CoSolver, CS2SA, and COCO, which stands for Cooperative Coordination Solver. In these methods, whenever a TTP instance is given initially, a heuristic called chain link learning on heuristic is used to generate an initial cyclic tour. Then the generated tour is processed by generating an initial collection plan. Then TSP solver and KP solver functions are called in an interleaved form to improve the generated solution and solve the TSP and KP components of the given problem. If there is not any improvement on the given solution and there is enough time, the whole search restarts by generating another initial cyclic tour. However, we found that for similar initial cyclic tours in these methods, the final objective value does not vary much. So the overall search for TTP involves redundant exploration of the solution space, and a subset of initial TSP tours will often lead to poor TTP solutions. Our proposal for these issues is applying a surrogate model for filtering out non-promising initial cyclic tours. As shown in this figure, after generation of any initial cyclic tour, it is given to a surrogate model, and the surrogate model predicts final objective value, which means the final objective value if the given tour would be processed. If the predicted final objective value is promising, then the given tour can be processed. Otherwise, it is filtered out as a non-promising initial cyclic tour. The proposed surrogate model is based on support vector regression, and it acts in 4 phases including initialization, training, testing, and applying phases. This figure shows these 4 phases with potential transitions between them. In initial phase, the given TTP instance is solved for a number of restarts to generate initial training dataset. Then in training phase, the final objective values in the training dataset are min-max normalized. Then the training dataset with normalized objective values is given to the SVR engine for training. The trained SVR engine can approximate normalized objective value, which means ng hat in this formula for any new tour. The kernel function k in this formula is a customized Gaussian radial basis function that measures the similarity between two tours. Finally, the approximated final objective value g hat is computed by reversing the min-max normalization on ng hat. In testing phase, the given TTP instance is solved for another number of restarts, and in each restart, the normalized error value is computed and the mean squared normalized error value is updated as a moving average measure using this formula. The SVR engine is retrained in this phase whenever a new minimum or maximum final objective value is obtained, if the MSNE value as the accuracy measure of the trained SVR engine would not be acceptable at the end of this phase. In applying phase, the surrogate model is employed for filtering of non-promising initial tours as expected, and for this purpose, the maximum tolerable error value or MT is considered to be beta multiplied by square root of MSNE, where beta is a hyperparameter. I will talk about this beta parameter in the experiments section. Any new tour is considered to be processed more if ng hat is larger than or equal to 1 minus MTE, Otherwise, it is filtered out either when ng hat is smaller than minus mte, or with a probability as shown in this figure if ng hat is smaller than 1 minus mte. The SVR engine in this phase is retrained if required, as in the testing phase, or more new tools are encountered. For more details, please see the paper. In experiments, we did a comparative evaluation between COCO solver, which is our proposed state-of-the-art TTP solver, with CocoSM, which is the same solver with the proposed surrogate model. Both solvers were run on HTTP instance 10 times. In each time, both solvers were run for 1000 restarts with the same initial tools. Experiments were performed with 4 different values for the beta parameter in computing MTE, or maximum tolerable error value. Benchmark instances were put in 3 categories, A, B, and C, being simple, moderate, and difficult to be solved. Each category has 32 instances with a range of about 600 to a bit more than 7,000 cities. This table shows results for the case with beta equal to 2. The first column shows names of the instances, and the next 3 columns show average percentage of the filtered out tours for each instance in each category, and the last 3 columns show the number of missed best solutions for each instance in each category out of 10. This table continues in the next slide, and as you can see in the last row of this table, around 1/3 of the tours are filtered out, but the average number of the missed best solutions overall instances is less than 1 tour, which means less than 10%. The next 3 slides show results for 3 categories. This is for category A, this is for category B, and this one is for category C. Here, these 4 points show performance of our proposed method with 4 different values for the beta parameter based on average number of the missed best solutions out of 10 in y-axis against average percentage of the filtered out initial cyclic tours in the x-axis, and this dashed diagonal line shows the potential performance of randomized filtering method. As you can see, in all 4 configurations, our proposed surrogate based filtering method performs much better than the randomized filtering method. However, when we decrease the value of the beta parameter from 3 to 0, the number of the filtered out tours increases, but it comes with the cost of losing more best solutions. Our aim in this research is to bring down this blue line and points down as much as possible, which means filtering more tours and at the same time losing less best solutions. As conclusion, we have proposed to incorporate a surrogate model for the cooperative TTP solvers to increase the efficiency of the search by pruning the non-promising starting points. The proposed surrogate model based on SVR, or supports vector regression with a custom kernel, adaptively learns the characteristics of initial tours leading to good TTP solutions. It detects and disregards non-promising initial tours. Experiments on benchmark TTP instances show that the proposed surrogate approach removes a considerable number of non-promising initial tours at the cost of missing a small number of the best TTP solutions. If you have questions, please contact me at the given email address. Thank you.